All right, thanks very much for having me. I'm going to be talking about the IsoDAR experiment, which is generously supported by the National Science Foundation, among others. All right, so the main IsoDAR's idea is we want to produce a lot of electron antineutrinos with an extremely well understood energy spectrum. That's not all. We're trying to kind of turn the for example, Fermilab paradigm on its head. Okay, where we the Fermilab paradigm being that we build a neutrino detector at a particle accelerator based complex. We study the neutrinos there. So the IsoDAR concept turns that on its head. So we want to actually, instead of build the detector at the particle accelerator complex, we want to take the accelerator and produce our neutrino source, our accelerator-based neutrino source, and put that next to a planned or existing deep underground ultra-large detector. Okay, so how do we produce our source of electron antineutrinos? It starts with a beam of protons from our accelerator, again, deep underground. It's really H2 plus ions, but we can think of that as protons. We shoot those protons into a beryllium-9 beryllium target, which is surrounded on all sides by a isotopically very pure lithium-7 sleeve. Okay, we want it to be isotopically very pure lithium-7 because we want to avoid lithium-6, which has a very high neutron capture cross-section and eats up our neutrons that are produced. Okay, so we want to produce a lot of neutrons. Protons hit this target, and neutrons are produced, and they eventually capture on lithium-7 to make lithium-8. Okay, so we get some lithium-8 production in our target, but most of the production actually comes from this lithium-7 sleeve. The neutrons slow down eventually and then capture on lithium-7 to make lithium-8. So the goal of this is to really produce as much lithium-8 as possible. And that's because lithium-8 beta decays with a half-life of about 1 second and produces a very energetic, at least for beta decay, electron antineutrino from about 0 to 14 MeV or so, as you can see in this flux spectrum, with a mean of 6.5 or so MeV. So as far as beta decays go, this is a very energetic electron antineutrino source. And when we put this, when we utilize the electron antineutrino source as is shown, we can show that the flux is really dominated by a single high Q isotope with a very well understood beta decay spectrum. Okay, so this represents a lot of neutrinos with a very well understood energy spectrum. Okay, so we want to take this electron antineutrino source and couple it to a big detector with free protons. We want free protons because we're going to be looking for inverse beta decay, where an electron antineutrino interacts with a free proton to produce a positron and a neutron in light-based, for example, liquid scintillator or Cherenkov-based big detectors with free protons. This gives a nice two-flash signal of your positron, which provides the electron antineutrino energy, and then the neutron capture sometime later, which provides the double coincidence of events that tells you that electron antineutrino interacted. Okay, and you can, for example, look for short baseline oscillations where the electron antineutrino rate is modulating as a function of baseline and energy, right, among other physics topics, as I'll go into. Okay, so this is the impetus, the really main impetus behind IsoDAR, which is we want to be able to see an oscillation wave, if such a wave exists, if our short baseline anomalies have something to do with oscillations or a sterile neutrino or neutrino decay or something like that. Okay, so to make a discovery, we really need to be able to map the oscillation wave, if there is one, just like we did with our 3 established flavors of neutrinos. You can see some beautiful examples from our historic experiments showing this oscillation wave. Yeah, we'd like to be able to at least have sensitivity to such a wave with IsoDAR. Okay, so here is an example oscillation curve that we might be able to see with IsoDAR. So it's observed over predicted electron antineutrino rate as a function of L over E. You know, for these example 3+1 oscillation parameters, delta m squared of 180 squared and sin squared 2 theta of 0.1, which is you know, reasonably consistent with the set of anomalies out there, Boone and LS&D, the gallium anomaly. This is you know, an example of a data set that IsoDAR would be able to produce. So you can see quite clearly that with these example, you know, representative oscillation parameters, that IsoDAR would be able to see the wave. Okay, so this is you know, IsoDAR's kind of capability to measure the oscillation wave under a representative oscillation scenario, which is, you know, reasonably consistent or characteristic with the anomalies. Okay, so the bottom line here is that, you know, if one or more of the anomalous short baseline results is due to new physics, IsoDAR will almost certainly make a discovery. And that's the real beauty, the real power behind this experiment, is its incredible sensitivity to L over E modulated neutrino behavior. Okay, that's not all IsoDAR can do in terms of physics sensitivity. IsoDAR will also be able to perform extremely sensitive search for new physics using electron antineutrino electron elastic scattering. Okay, where you know, this is a very well predicted standard model process. It's in, you know, any number of the textbooks that we open up. You know, a purely leptonic process, you know, it has contributions from the neutral current and the charge current, and you know, just looking at this cross section as a function of, you know, outgoing electron energy, for example, is highly sensitive to new physics having to do with the electroweak sector. Okay, so we are yeah, we're trying to make this happen. We've been supported by over a decade by you know, the NSF, Heising-Simons, and universities, and we're also now supported by the DOE as well to establish the cyclotron and target, and to also utilize this machine in an attempt to make medical isotopes as well. You know, we've received awards for the design from Accelerator Physics and the APS-DPF instrumentation award as well. And yeah, this is the scheme we've come up with for producing this electron antineutrino source over the past decade or so. We start with an ion source producing H2+. We actually use H2+ because you know, this is a, you know, 600 kilowatt beam of protons, and you know, space charge is a big concern inside of this the cyclotron, which gets the H2+ up to 60 MeV. And so for you know, reducing space charge, we have you know, we accelerate 2 protons for only 1 unit of charge, pushing the, you know, the beam apart. That's why we use H2+. Okay, so we've come up with this cyclotron driver, this medium energy beam transport system, and then, you know, this target and sleeve, which represents the actual source of neutrinos. And then our current plan is to couple this accelerator neutrino source combination to the LSC, the Liquid Scintillator Counter 2 kiloton detector in Yemilab, in about 1 kilometer down in South Korea. And just to note that this, you know, much of the work so far on IsoDAR has been in the cyclotron driver, 600 kilowatt cyclotron, which has about a factor of 10 times more power than on-market machines, which again represents a very valuable spin-off for our field in producing medical isotopes. And there are some other ideas for how to use this kind of machine for science and for society. Okay, so yeah, I mean, there's a number of great advantages of this concept over others. This is really a beyond standard model physics experiment, extremely sensitive in a number of ways. Basically, you have a single well understood decay, so you know what your neutrino spectrum is very precisely. It's enormously powerful, about 10 to the 24 neutrinos in 5 years produced. We have a peak at relatively high energy, noting that, of course, the inverse beta decay cross-section is increasing with energy. It's negligible beam background. It's deep underground, so cosmics you don't have to worry about very much. Very well understood primary neutrino interaction process, which is inverse beta decay with 1 to 2% cross-section uncertainty. There's also the Neutrinos electron elastic cross-section, which is similar, if not less, uncertainties as well. Very high production rate, and then we can also turn it on and off as well. Okay, so yeah, we're trying to pair this with a 2.5 kiloton liquid scintillator counter detector, the LSC, deep underground at Yemilab in Korea. Here is a semi-realistic view of the cavern, which holds the cyclotron and the 60 MeV proton beam transport, and then the electron antineutrino producing target and sleeve. Noting that the beam, we plan on having the beam pointed opposite to the detector. You can see the 180-degree beam bend targeting protons towards the upstream of the detector. And then this source is going to be about 17 meters away from the center of the LSC. Okay, so we actually have a cavern, IsoDAR cyclotron cavern. You can see it, the hole right here. It's a real camera image deep underground in Korea. And then we've put the CAD model of the cyclotron inside of this cavern, and yeah, we're hoping to obtain funding for the full experiment and take data in the next few years. Okay, just to give you a feel for the BSM sensitivity, we really designed IsoDAR with oscillations in mind. So IsoDAR provides really extraordinary sensitivity to short baseline oscillations in whatever form you can think of. We'll get about 1.7 million inverse beta decay events in 5 years, again with a known, very well understood flux, very well understood cross section, and within a 3+1 oscillation model, you can see the IsoDAR Yemilab 5-year 5 sigma sensitivity in this delta m squared versus sine squared 2 theta e parameter space. You can see that we are really quite sensitive. If any of the anomalies are due to new physics involving oscillations, IsoDAR will be able to see it. In case there is some other exotic model at work in nature, a 2 sterile neutrino model or a 3+1 decay model, again, IsoDAR will be able to see it. Okay. The bottom line again is that if any of the anomalies is due to oscillations, almost certainly IsoDAR will be able to tease out what it is, and not only that, provide a smoking gun signature, a wave measurement of that signal, and make a discovery. Okay, IsoDAR will also, like I said, collect about 7,000 Neutrinos electron elastic scatters in 5 years. This is about a factor of 7 or so higher than it has been detected worldwide. Okay, so we're going to collect a lot of many thousands of events of this incredibly interesting process that is very well predicted by the standard model. You can see kind of our expected event rate versus visible energy for the Neutrinos electron elastic signal in green, and then our expected backgrounds in black. And you can see for a large range of visible energies due to the electron, our signal is well above the background. So with this sample, we will provide an excellent precise measurement of the weak mixing angle at a low Q value, which was actually fairly competitive with atomic parity violation measurements, measurements of the weak mixing angle in a different sector. And you can see that we're going to vastly improve upon the global reactor electron antineutrino measurement to date. And then we also have some sensitivity to non-standard neutrino interactions where we're sensitive by looking for a deviation in the expected cross-section. And you can see that in this plot here, where the expectation is that there is no NSI contributions at all. So the expectation is that it's 0, but in case there is something funny going on in terms of these couplings, we will be sensitive to it. Okay. We're also sensitive to low mass scalars. For example, you shoot 10 to the 23, 24 protons out of a piece of metal. Maybe you make something exotic like a low mass scalar, and then you might have a decay where the decay produces an antineutrino. Well, electron antineutrino can enter your detector, interact, and that would maybe create a peak in your measured inverse beta decay spectrum. So you can see our sensitivity to a new scalar in this plot. Also, you might make an axion-like particle. If the axion couples to nucleons, electrons, or gammas, and then enters the detector, and then produces one of these different signatures involving single gammas, diphotons, electron gamma, or electron positron pair, we might be able to see that as well. IsoDAR makes a lot of excited nuclei, of course. So if there's an axion-nucleon coupling, then you might get a peak at one of these particular energies in your signal. And if you work it out, IsoDAR actually has competitive, if not leading, sensitivity to a number of these couplings in pretty significant ranges of axion mass parameter space. You can see that axion electron coupling versus the mass of the axion here, and you can see how well IsoDAR does compared to others. Okay. We've made, I'm running out of time, I only have 40 seconds left, but we've made an enormous amount of progress in accelerator development. You can see the different elements of the accelerator. The top two and the bottom left are either exist or being built or are funded. And then our full cyclotron design is on the archive. And then we're building the neutrino source as well at the University of Michigan. Yeah, thanks for your time. This is a very exciting experiment, and I hope you know a little bit more about it now. Thanks.